All right, hello everyone. Today we'll be going over chapter 15, radical reactions. And I'm going to specifically be going over the topics that Dr. Dowdy has for us, or has listed for us, specifically for the quiz and the final. So I may be skipping over a few things. I just want to make sure to hit everything that he talks about in his little list over here. The first thing he talks about is homolytic cleavage of nonpolar covalent bonds. And we usually see that represented by A attached to B, and we'll see that bond break homolytically. Now, a quick review about what homolytic and heterolytic cleavage is. Heterolytic cleavage is when all the electrons of a covalent bond break and go to a single side of that bond, okay? When we talk about homolytic cleavage, we have one electron from that bond going to each side of the bond. So in this first example here, this is going to be our heterolytic, I'm just going to put hetero here, our heterolytic example. So what happens is we end up with ions A plus B negative, where B has an extra set of electrons. The second one here is homolytic cleavage. I'm going to write homo there, and we end up with two radicals, A radical and B radical. And notice how these two don't have charges, and that is because neither one of them has a full electron pair, and neither one of them is missing a full electron pair. So that's why we show single bonds or single electrons rather than a plus or a minus charge. In addition, in homolytic cleavage, we can see here that we use these half-headed arrows. The way that I like to sort of think about this in my mind is that a full-headed arrow carries two electrons, one on either side of the barb, whereas a half-headed arrow only can hold one electron, and so that is why we use half arrows to show the movement of a single electron rather than full arrows to show the movement of a full pair of electrons. All right. So what we're going to be talking about now is homolytic cleavage, because we're going to be talking about radicals. And one thing to note when we talk about radicals is when we talk about a carbon radical, basically we'll be talking about a carbon with four bonds, four single bonds, two double bonds, whatever, with a radical. And we consider this carbon sp2 hybridized, which means it's going to be trigonal planar. And this will come up later. We'll talk about this a little bit later. I just want to mention it right now. Whenever we have a carbon radical, we consider it sp2 hybridized and trigonal planar. All right. So now let's talk about the stabilities of radicals. So similar to stabilities of carbocations, when we have a carbon radical, the more substituted it is, so if it's not substituted at all, if it's a methyl carbon radical, it's going to be less stable than a primary carbon radical, which is less stable than a secondary, which is less stable than tertiary, which is less stable than something called an allyl radical. I'm just putting allyl dot. And what that means essentially is we have a double bond which is next to a carbon that contains that radical. And the reason why this allyl radical is so stable, or so stable, is that it has a resonance structure where this double bond sort of flip-flops over here to combine with the one electron that creates the radical, and the other electron from that double bond goes to the other side of the double bond, and we end up with a resonance structure here, which makes this allyl radical very stable. And another thing to note about the allyl radical is that if we have a secondary allyl radical versus a primary allyl radical, so this second example here I'm drawing, I'm going to leave out the arrows here, but we can see here that when we look at this second radical here, we can see that this is a secondary compared to a primary radical here. So overall, this one would be considered more stable. Okay, and so that's just a quick example of the stabilities for these different carbon radicals. Okay, and so the next thing he wants us to talk about is the halogenation of alkanes. And notice here, alkanes, A-N-E. So we're talking about carbon-carbon single bonds. So these are reactions with sigma bonds of those radicals. And the reason why this is so important is this is the first time we can actually see a reaction occurring with the alkane and producing something else. So this is called the halogenation of alkanes, and the general overall reaction scheme for this would be we have a carbon with 3 bonds with a hydrogen reacting with either an X2, which is either going to be chlorine 2 or bromine 2, in addition with light, which is represented by HV, or heat, which is represented by this triangle here, and we end up replacing that hydrogen with whatever that X is. So that would be a chlorine or a bromine. So we can see here, now we have a way of creating an alkyl halide from an alkane, which we haven't had before. Okay, and so now let's talk about the general mechanism for this. So when we talk about this mechanism, we split it up into 3 parts: initiation, which I'll represent by I, propagation, P, and termination, T. Okay, so the way that I like to remember these is that initiation starts out with 0 radicals, and then we end up with 2 radicals on the product side. So what will happen is, let's take bromine, for example. We'll have bromine attached to a bromine, no radicals on this side. And then what will happen is we introduce light or heat or whatever. And then what happens is that the radicals, or not the radicals, but the bond between them will break. And we end up with 2 bromine radicals. Okay, so this is initiation. We start with 0 radicals, we end up with 2 radicals. Propagation, we start with 1 radical, we end with 1 radical. A good example of this, I think, in the PowerPoint is when we have this cyclopentane with the hydrogen here. And what will happen is one of those bromine radicals will come in and sort of steal that hydrogen. So what will happen is one of the electrons from the hydrogen carbon bond will combine with the single electron from the bromine and will create a new bond. And then the remaining electron on that bond will then add to that carbon, and we end up having a carbon radical plus HBr. So we see here, we start with a bromine radical, we end with a carbon radical. We have 1 radical on one side and 1 radical on the other side. And this will usually be followed up with an additional radical propagation, but let's just ignore that for right now because I want to keep this as simple as possible. Let me move this termination. Hold on, let me move this termination over here so it's a little bit clearer. So termination, we start out with 2 radicals and we end with 0 radicals. So this is the opposite of initiation, kind of. And so what will happen is, let's say that we have our carbon radical from before in conjunction with a bromine radical from before. So what will happen is that the single electron from the carbon radical and the single electron from the bromine radical will combine, and we end up with our final product with 0 radicals. And this termination can include 2 bromine radicals coming together to make a new bromine-bromine bond, or it can include 2 carbon radicals coming together to make a carbon-carbon bond. As long as you go from 2 radicals to 0 radicals, that is considered a termination reaction. Okay, so that's the general mechanism: initiation, propagation, termination. So now let's talk about chlorination versus bromination. So before we sort of discussed about whenever we do halogenation, we use X2, and that X2 can either be Cl2 or Br2. So depending on if we use chlorine or if we use bromine, we are going to end up with slightly different products, slightly different ratios of products, to be more precise. So let's take the example. Let's say we have propane. And if we do chlorination, so if we use Cl2 along with HV or delta, then we'll end up with an equal amount of 1 propane and 2 chloropropane. Let me draw that here. So we have a 1-to-1 ratio. We make equal amounts. However, if we did the same thing, except instead of chlorine, we use bromine, we are going to end up with more of the, we're going to end up with less, rather, of the primary alkyl halide than the secondary alkyl halide. So there's going to be about 99% of this one versus 1% of this one. Okay, and the reason this has to do with sort of the reaction, the energy diagram for each of these reactions. So if I were to draw the reaction diagram out here to the right, we can see if I went ahead and drew the chlorine reaction mechanism, we would see two, hold on, let me draw in different colors actually. We would see two reactions here. Let me use blue. We see two reactions here. The red one, the red line represents the primary alkyl halide, and the blue line represents the secondary alkyl halide. We can see here that the starting point, they're going to be the same. They're going to be relatively the same. And then if we look over here at the transition states, we can also see those are similar in energy. And so both products are going to form since they have about the same activation, or not the, activation energy transition state. However, if we talk about the bromine, we can see here that the red version, which is the less stable version, and then the blue version, which is the more substituted version, is going to end up with slightly different graphs. So for the bromination, we end up, oh, I'm sorry, I drew this slightly wrong. Let me redraw that. The bromination would look like this. So we can see with the blue, with the more stable alkyl halide, we have a significantly lower transition state and more stable products. And it's the same with the, I'm sorry, it would be the opposite with the less stable, a higher activation energy, a higher energy radical intermediate. And so this overall is kind of why the chlorine doesn't care too much about which product it forms. It will overall tend to form the more stable product more often. However, that ratio is going to be much closer than the bromine ratio. So overall, the chlorination will tend to form more equal amounts of each product, and the bromination is going to be far more selective and form the more stable product overall. Okay? And the whole reason for this is if, again, we look over at this reaction diagram, we can see that the chlorination, that the reactants are closer in energy to the activation energy than the intermediates, whereas it's the exact opposite for the bromination. And so we can see here, because of the stability of the transition states, that is going to influence which product is going to be formed. So with chlorination, it's less picky. With bromination, it's very picky. Okay? And so the next topic on this list is going to be the stereochemistry. Okay, so I'm going to go ahead and erase this, and now we're going to talk a little bit about the stereochemistry of halogenation. Okay, so let's take the example from the PowerPoint again. This propane plus Cl2 plus HV or delta. And again, we are going to get two different products. This product here or this product here. Okay, so if we look at the first product, we'll call this product A, and then we'll call the second one product B. Product A does not have any stereogenic centers. We see here that the carbon that the chlorine adds to still has two hydrogens, so that carbon does not have four different groups around it, so it cannot be a stereogenic center. Actually, I'm going to alter this slightly, so I change this into a butane instead of a propane, so we can actually have a stereogenic center for product B. And so then we can see in product B, we have a stereogenic center. We have four different groups surrounding that carbon. As a result, we have to express stereochemistry. And when we do a radical reaction, we are going to end up with two enantiomers as our product. One where the chlorine is going to be in a solid wedge, and then one where the chlorine will be on a dashed wedge. And this is because, if you recall earlier, we talked about how the radical intermediate will be sp2 hybridized. Remember, when we're sp2 hybridized, we're trigonal planar. And so it's going to be open to front side or back side attacks. If you recall, with the alkene reactions, whenever we created a carbocation intermediate, we had either front side or back side attacks, and we ended up with both enantiomers, and the same thing happens here. Okay? One thing to note is that if we end up already having an enantiomer, so like or not an enantiomer, but a stereogenic center to begin with. So let's ignore product A for right now. Let's just delete that really quickly. And I'll move over this guy. So let's say that we already had a stereogenic center, like right here. So let's say we had like a bromine or something. That stereogenic center is not going to be changed throughout this chlorination. the only stereogenic center that's going to be influenced by this halogenation, whether it be chlorination or bromination, is the stereogenic center, or the carbon that it is attacking. So we see here we end up with two diastereomers because these two stereogenic centers stay exactly the same. Okay, and so then that's sort of a rough idea about how the stereochemistry works. Okay, and so now let's go back and let's talk about the allylic radical. So again, an allylic radical is basically when we have a radical next to a carbon-carbon double bond. And so when we have an allylic radical, what will happen is that that radical will be preferred for halogenation. So for example, in the PowerPoint, they have this guy right here. Okay, and then they have three different hydrogens attached to it. They have this hydrogen here, um, this hydrogen here, and this hydrogen here. So hydrogen A, hydrogen B, and hydrogen C. Overall, if we were doing chlorination, bromination, any halogenation with this guy, hydrogen B is the one that's going to be preferred to be replaced for the halogenation. So X would go there. And this is because this hydrogen, this is an allylic hydrogen. So if we get rid of this hydrogen here, we are going to end up with an allyl radical, and as a result, it will be stabilized by resonance, and so then that radical is going to be far more stable than if we attacked hydrogen A or hydrogen C. So that radical is going to be the one that's going to be preferred for the halogenation. Now, one more thing to note for this allylic halogenation, let's say that we have, I'm going to go ahead and draw, let's say we have this guy right here. Okay, so we have a double bond there. Actually, let me move the double bond right here. So we have a double bond here, and we have two possible points for a radical allyl, or an allylic radical. That would be this carbon here or this carbon here. And again, if you recall, the green carbon is going to be the one that's going to be preferred to put the lone electron on than the pink carbon here. And that is because, again, we prefer more substituted carbons. So I'm just going to go ahead and do that. So we put the radical right here. Okay, but then what can happen is, again, we have those different resonance structures. So the resonance can move, and we end up having our double bond right here and our radical right here. Both of these different allyl radicals can react to do that halogenation. So we end up with two different products. And again, there would be stereochemistry, but right now I'm sort of ignoring that to rather show you what's actually happening in these reactions. So we have these two different products. Both of these will form because of those resonance structures, and that's important to note. So when we do allylic halogenation, we can end up with two different products because of the allyl resonance structures. Okay? Okay. And so the next thing on this list is going to be talking about, again, this is talking about the mechanism. The mechanism is going to be relatively the same. It's just sometimes you're going to see NBS used rather than BR2. And the reason why we use NBS over BR2 is because in real life, BR2 is a pretty dangerous chemical to have around. NBS is far more stable, so you'll tend to see that in experimentation. And so then you'll see that when we talk about the mechanism here, at least in the PowerPoint. Okay? So the mechanism is going to be very similar to what we had before, with initiation starting with the NBS, basically with light giving off a bromine radical, along with another radical, but the bromine radical is what we're focusing on here. And then the propagation basically occurs through the, so I'm going to use the example in the PowerPoint, where we have our our double bond here with a hydrogen here, our allylic hydrogen. That's going to be attacked by our Br here, and we're going to form our new bond through propagation. And then we end up with our allyl radical along with HBr, which is just sort of left over after everything happens, which is followed then by another propagation step where we end up having our final product. And again, termination will occur. It's just not drawn in this instance because it's basically to save room. But again, whenever we use NBS, this is basically what's happening. We do the initiation just like before, we do propagation just like before, and then termination will follow. Usually, at least usually in this case, we would have two bromine radicals interacting and then becoming a bromine-bromine bond, okay? And so that's the general mechanism. Again, it's very similar to how the mechanism works for the regular halogenation, okay? And so the next thing that he wants us to talk about here is going to be radical inhibitors. Okay, so the way that I sort of think of radical inhibitors is they sort of, so I'm going to take the example from the PowerPoint again with the hydroquinone. So we have this guy here with OH and OH. So if you notice here, I know we didn't talk about it in this session here, but if you notice here, we can see that this oxygen is going to act like a benzylic carbon, aka an allylic carbon on steroids. So we see here that this oxygen connected to a bunch of double bonds is going to be very stable if we put the radical on it. And if we say, oh, we have a carbon radical over here, that carbon radical is going to be far less stable than that oxygen radical. So what occurs is this carbon basically steals that hydrogen, which is called hydrogen abstraction, basically steals that hydrogen, and we end up with this radical right here. So this radical is really stable because it has a bunch of resonance structures that I haven't drawn, and I'm not going to draw here because that would take up a bunch of time. But this guy has a bunch of resonance structures, so it's super stable on its own. And this will occur with most radical inhibitors. And basically what these radical inhibitors do is they sort of soak up all of the radicals around them. And if you've ever taken a biology course, we have a bunch of these in our bodies, like vitamin C. So vitamin C or vitamin E are good examples, where vitamin C works in water and vitamin E works in organic solutes, okay? And so those are some good examples of radical inhibitors. And just remember, if you have a radical inhibitor, it's going to hog all of the radicals towards itself. It's going to stop any other radicals from forming because it's going to steal those electrons for itself. And so it inhibits any radical reactions, okay? Okay. And so the next topic that we're going to talk about here is going to be radical addition. So as the name implies, this is going to be an addition reaction. So we're going to go from a double bond to two new single bonds. Okay, just like the name implies. However, from before, if you remember before when we did these types of reactions, when we did the double bond, we always did it using an ionic reaction. And in this case, that would be, okay, so let's say we have this guy here, we have HBr. We would use ions. Actually, let me change this. We'd use ions, and then we'd end up with our product looking like this. Noticeably, the hydrogen adds to the less substituted carbon, because of the Markovnikov rule, which I hope you remember from the alkene chapter. If not, then go ahead and review that. But again, the hydrogen will add to the less substituted carbon because of that Markovnikov rule. However, if we use a radical instead of so if we have HBr along with light, heat, or a peroxide, which is going to be ROOR. Again, something to note, that peroxide, ROOR, is not a peroxy acid, which is RO3H. The peroxy acid does epoxidation. The peroxide does the radical reaction. Okay. All right. So if we see HBr along with one of these other reagents, what will happen is that hydrogen will then add to the more substituted carbon rather than the less substituted carbon, and we add anti-Markovnikov, okay? And so this is the big importance of this radical addition reaction. It's because before, all we knew was how to do Markovnikov addition. Now we can do anti-Markovnikov addition using this radical addition. And so let's explore the mechanism very quickly for this and why exactly it does that Markovnikov addition. So we're going to start with our ROR. I'm just going to use HOOH. And so initiation. Again, we always start with initiation, and what will occur is that this will spontaneously form two radicals, which will then cause HBr to break apart into a new, the radical that we're looking for, which is the Br radical here. So that's our initiation. Technically, if you followed the rules from before, if you followed, if we start with no radicals and we end up with two radicals, that's initiation. That would be this step right here. The only reason why we don't really consider that alone the initiation is because that's not actually what we're after. We are after this bromine radical. So that is why we consider this whole thing initiation rather than just this first step. And then, of course, initiation, as always, is followed by propagation. And what will occur is we have our double bond here and our bromine radical here. What will occur is that one of the electrons from the double bond will combine with one of the electrons from the bromine, and then the extra electron from the double bond will end up going onto the carbon that will cause it to be the most stable carbon radical. So in this case, that would be this one right here, this secondary. And this is why we add anti-Markovnikov, because now the place that the hydrogen has to add to is that carbon with the radical. And so that is why we add anti-Markovnikov, because we want to form the more stable radical. And to do that, we have to add our halogen to the less substituted carbon. And so then this propagation is followed by HBr being added onto it, like we did before, where this attacks here. We form a new bond and we form a new radical. And so then we end up with our final product. And again, this will be followed by termination, but I'm not drawing that now to save time. Okay? And so that is why we add anti-Markovnikov. And so this is important to note because this is the only this along with hydroboration oxidation are the only two reactions that we really know of that are going to add anti-Markovnikov. So if you want to add a bromine anti-Markovnikov, you're going to be doing this radical addition reaction. Okay? Oh, that's the wrong thing. That's not what I want to do. But let's erase this. And so the next thing that we are going to talk about is polymerization. So polymerization is basically taking a single monomer, whatever that be. So a monomer could be ethylene. That's the first example we see in the PowerPoint. So an example here would be ethylene. And then so this monomer is going to chain up with other monomers to make a polymeric chain of that monomer. So we can see that here. Okay? And so we can see that the actual chain here, or the actual monomer, is consisted of this first part here. And that's sort of how I like to sort of break down these different monomers versus polymers. The monomer, what will happen is we have our monomer here. We see we have a carbon attached to a carbon by a double bond. What will happen is one of the bonds in the middle will break, and then that bond there will sort of unfold to create additional bonds onto the carbons that used to be part of that double bond. This will make more sense when we do more examples. I just want to give you a quick rundown of this. So how exactly does that whole process happen? Well, obviously, since this is the radical chapter, it's going to happen through a radical reaction. And essentially what occurs is we use our ROOR, our peroxide, which spontaneously forms two radicals here, which then will cause our polymer, so in this case, our carbon-carbon double bond, it will cause it to become a radical. So a carbon here and then a carbon radical here, because that double bond broke to create a new bond with the RO, and then that extra electron had to go somewhere. It went on that carbon. And so then the propagation, so here's initiation. And so then the propagation is just going to be the growth of that polymer. So now we have our radical here. And so then what it's going to do is it's going to attack the next monomer, and then create a new radical. And so then this will continue on and on until it's stopped by something, until it meets another version of the polymer. So the termination occurs when we have one version of the polymer right here. I'm just going to do it short for my sake. And then another version of the polymer here. So then what happens is they come together to make a new bond, and then that's what ends the polymerization. Okay? And so that, in a nutshell, is sort of how we actually do this radical polymerization. All right? So let's continue on and sort of let's talk about how can we tell what is going to be our polymer, what is going to be our monomer. So one example in the PowerPoint, again, I'm referring back to the PowerPoint, is going to be that vinyl chloride, this one right here. So the way that I would do this is I would go, okay, first what I'm going to do is I'm going to number all of my atoms here. So I have 1, 2, 3. So my monomer is going to consist of 3 atoms. And then I'm going to highlight my double bond and the carbons attached to it. And so then I'm going to say, okay, so when that double bond breaks, so I'm going to redraw this. So I'm going to redraw this with a single bond. 1, 2, 3. When that double bond breaks, the new connecting bonds are going to go on either carbon that used to be a part of that double bond. So it's going to look like this. So if I were to redraw this in a sort of way that is more familiar to us, it would look like this, right there. And then we'll count again. 1, 2, 3. Okay, great. My monomer is still intact. And then essentially what you would do from there is just continue adding more monomers. Okay? And so then this is your polymer. Okay, and that's going to be shown like this. Now, of course, those bonds won't be highlighted, so you're going to have to find them on your own, but that's the general gist of how to go from a monomer to a polymer. But to go vice versa, it's going to be a little bit more complicated. So again, I'm looking at the PowerPoint, and I'm going to be using the example of polypropylene. So we've got this guy right here. Okay, so we have this one right here. And so when we're trying to figure out, okay, so what exactly is going to be my monomer that makes up this polymer? What you're going to do is you're going to try and find that repeat unit. So if I look at this for a second, I say, okay, so I see that this unit here is being repeated over and over and then linked by this single bond here. So that is probably going to be what makes up my monomer. So now I'm going to redraw it. So I only have one of the monomers present along with the expanded double bond. And so then what I'm going to do is I'm going to say, okay, so the double bonds that are linking this whole polymer together are on this carbon and on this carbon. So those 2 carbons must have been the ones with the double bond. And so then there is the monomer that started everything. Okay? And so that is all of the topics that he has listed for you to know from chapter 15. I know I went through it very fast, but I want to get this video up as soon as possible because I know you guys have a quiz tonight. So just let me know if you have any additional questions, and I'll see you guys next time.